Good afternoon, ladies and gentlemen. Welcome to TechGeek webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is Intelligent Power Management of IT Infrastructure. Our guest speaker today is Mr. Srinivas Varadarajan, CEO, Vigyan Labs Innovations Private Limited. Mr. Srinivas is the founder and CEO of Vigyan Labs and has 20 plus years of experience in the IT industry. In the past, Srinivasan worked with Hewlett-Packard, Perot System, and held very senior positions in the organizations, leading engineering teams that build systems such as Amadeus and eSpeak among others, HP eSpeak among others. Recently, Srinivas was one of the key IT architects for the Aadhaar program and has also served the Indian Air Force in design of biometric systems. Srinivas holds 4 patents, including his latest one for application sensing. Power management of IT infrastructure. He holds a MTech from IIT Bombay. So without any further delay, I introduce you all to our guest speaker. Over to you, Mr. Srinivas.
Good afternoon, everybody. The topic of today's webinar is Intelligent Power Management of IT Infrastructure. Let me just go through the agenda. So in the webinar today, we'll be covering the following areas. Look at IT and energy, how much energy is spent by IT and where and how spent. What are the things driving the change in IT? So what is causing IT to change? And what's the impact of that on energy as well as environment? Another important part of IT is the data center. What is the road ahead for the data center? What are the changes happening today? And what do we see changes happening in the near future? Next, we'll talk about the business case for intelligent power management. Why do we need intelligent power management? And what are the drivers for intelligent power management? And last, we'll conclude by looking at why do we need savings? What is the impact of savings on the top line, bottom line? Of course, the overall global environment and environment impact. Before we go into details in looking at IT and energy, it's very, very important to understand how much of power is consumed by various kinds of equipment. Just have a look at this slide. Try to capture here various equipment we use, in our offices or partially at homes, offices, and how much power does it consume, and what's the impact on the environment. Let me just go through the few of the commonly used equipment. Let's look at typical desktops. A desktop consumes between 1 or 1.5 incandescent bulb equivalent of power, and an yearly consumption is about 289 kilowatts, which translates to around about 100 plus kgs of CO2 emissions. So to absorb that amount of CO2 emissions, you need to actually grow at least a tree, minimum a tree can absorb that one. Maybe a server. So there's a difference between the server and the desktop. Servers, although you have wide variety of models, there are vendor specific, there's a commodity servers. And if you just take a simple server, an average, running a server, and typically servers are kept on 24/7, 365 days a year. Look at typically about 6 incandescent bulbs, 1750 kilowatt hours, 1000 kg or equal to 1000 plus kg of CO2 emissions. You also have you need to grow plenty of trees to absorb the CO2 emissions of a single server. So similarly, you look at a network switch, laser printer. So one is energy consumption and one is the total yearly energy consumption. So why do you see the difference here between a laser printer, a projector, a network switch, and a server? Typical laser printer, is not kept on all the time. Goes into a sleep mode very often. A projector itself is also not kept on. A network switch is typically kept on most of the time as a part of your IT infrastructure. Servers are kept on desktops are sometimes people do turn off, sometimes people do forget to turn off. Let us look at this from a different perspective. The various other equipment, electrical equipment, how much power do they consume? We use the unit of watt hour, right? 1 watt, basically if you consume 1 watt for 1 hour, it's 1 watt hour. And we see the emergence of tablets as, the end computing devices today. How much power does a tablet consume? Is about 10 watt hour. So if you use a tablet for 1 hour, doing something, watching a movie or checking your emails or blogging, typically it's about 10 watt hours. That means 10 watts for 1 hour. These numbers may vary depending on your tablet, brand, model, and make. I just taken an average number. Similarly, if you run a fan for an hour, you consume about 35 watt hours. An incandescent bulb is of 60 watt hours. A PC desktop, 80 watt hours. A LCD TV, a 32 inch is about 100 watt hours. So put in perspective, many of these home consumer equipment consume probably less than many of the significantly less power than the IT equipment. Let me go ahead and look at how much energy do you consume globally. Electrical energy, I mean the electrical part, electrical energy only. If you look at the World Bank report on the energy consumption as of 2009, so it's about a couple of years earlier, but you can as well extrapolate the growth and see how it is today. A global energy consumption in 2009 as per the World Bank report is 18,500 terawatts. Terawatt is huge, right? We have a kilowatt, 1,000 watt is a watt hour is a kilowatt hour, 1,000 kilowatt hour is 1 megawatt hour, 1,000 megawatt hour is 1 gigawatt hour, so 1,000 gigawatt hour is 1 terawatt hour. So you are saying 18,500 terawatt hour. It means you are running so much, you are consuming so much of power. And in comparison, let us look at the IT part of this, like the data centers. The data centers are basically the sites which power the servers. For example, Google has its own data center, Yahoo, Google, Facebook, LinkedIn, everybody has their own data centers, and data centers host servers, storage, other equipment for all these applications to run. So as for the latest census from the data center dynamics, the global data center power consumption is about 322 terawatt hours. It is sort of a small percentage of the global electricity consumption, but nevertheless, it's a significant part. Look at the country-wise electricity power consumption, right? What the power consumed by the data centers worldwide is enough to power the entire of Russia. Most of the Russia can be powered by the 322 terabytes of power, which is a huge number. And let us look at the other set of devices which are coming to the market today. We have seen tablets literally everywhere. So look at the estimate of tablets in the world by 2015. There are going to be 350 million plus tablets in the world. And the total energy consumed by the tablet itself is 3 terawatt. How much is 3 terawatt? 3 terawatt hour of power. The 3 terawatt hour of power is sufficient to power 1.5 million houses or 15 lakh houses for 1 year. So although these tablets, smartphones consume a small amount of power, they are growing in huge volumes. Every house has a couple of tablets, every office has hundreds of tablets. So although individual power consumption is low, because of the sheer volumes of numbers, aggregate power consumption is very, very high. So you can talk about IT vendors, the chip manufacturers saying my chips are more efficient, more good, but again, they are becoming more powerful and they are also becoming more feature rich. We had many years back we had simple mobile phones, today we have smartphones, more functionality at the same time, consume more power. So these IT devices which are small, powerful, become very, very pervasive. And of course, aggregate, they consume a lot more power. Let us look at what is happening in the entire industry itself. What is driving change? We as consumers, I mean all of us, we are buying more and more equipment, smartphones, smart TVs, mobile phones, tablets, and these are being bought in millions and millions, not small numbers. We also use a lot of rich media, play with YouTube videos, access the social network all the time, typically keep the network on, do online reservation systems, online bookings. We as consumers are driving a lot of things. We are using more and more network bandwidth. That's why the telecom providers are providing 3G, 4G, and you will see LTE, higher and higher bandwidth network. And of course, there's also cloud computing already in place. And When you access these services, many of these services are hosted in the cloud, and finally the cloud services require data center to host. So we as consumers are actually driving the change of creating more and more data centers globally. So data centers have servers, storage, networking. Of course, you need power to power all the servers from the grid. There's low power, you need huge generators, UPSs. You need massive cooling equipment to cool all the heat generated by IT equipment, so on. And what's the impact on the environment? Look at, we are already talking about recession globally. Right? Last couple of years, the global economy has gone down. We are in this low single-digit growth. Look at the global GDP growth; it's a low single-digit. But what about the pollution we are causing? Look at the McKinsey report. But from 2007 to 2020, the projected growth is about 11% in the CO2 emissions. We're not talking about tons; we are talking about megatons of CO2 emissions, which has a huge impact on the environment itself. Let's go into a little more detail on the various factors which are driving this change. Let's look at the projected growth of smartphones and the tablets. See, as per the 2011 estimate, we had about 260, 270 million smartphones, expecting 1 billion smartphones to be there in the world by 2015. Just imagine 1 billion of these devices, each of them consuming 5 to 10 watt hours of power, roughly. You straight away have billion, watt hours of energy being consumed just by these phones. And similarly, the tablets, right? The projected growth rate of tablets is about 350 million by 2015. So just as I talked about, these tablets and smartphones itself has a big impact. Although they consume small amount of power by unit, but the sheer numbers in millions and hundreds of millions together, they consume a large amount of power, which itself has a big impact on indirectly impact on the environment, because large number of smartphones devices themselves consume power directly. Indirectly, they use the network, and the network provider has to add more and more equipment. All the service providers like Facebook, Googles, and the Yahoo's of the world have to add a lot more servers, storage, because every day we are adding more and more content. And to keep all this content and power all these servers, we need a huge amount of power. We as a consumer actually are driving this change, and our devices actually are driving huge increase in CO2 emissions and consumption of power. Let us look at how much of data we have. Every year you must have seen, we had, once upon a time we had megabytes of disk. We have gigabytes, we have terabytes. And the disk size capacity is increasing. On average, look at last decade, year on year, the capacity of a single disk is increasing by about 40% every year. Although disk capacity is increasing 40% a year, the content is increasing at a much faster pace. We always, once upon a time we said, 20 MB of a disk was very good enough for us. I'm happy with it. But today I think many of us have a terabyte of disk on the desktops or the laptops. We still find it's insufficient. So globally, if you look at the storage capacity worldwide, it's in exabyte. So what's an exabyte? We have, 1000 kilobytes is a megabyte, 1000 megabytes is a gigabyte, 1000 gigabyte is a terabyte, 1000 terabyte is a petabyte, and 1000 petabytes is a exabyte. And these systems globally, if you were to put together in a system, just look at the amount of space it takes globally. Land, right? Look at the land. Just the acreage space for a data center storage for these devices itself is thousands of acres. We need thousands of acres of data center space just to host this data. Where is the data coming from? We are all creating, right? Putting more and more YouTube videos, Facebook pages, Twitter tweets, emails. This is excluding the corporate data, where again we create tons and tons of data for all our business applications. So we are consumers. As consumers, we are having more and more smartphones, tablets. We probably have, near time we'll be having a few smartphones at home, few tablets at home. Increased number of smartphones has an impact on the telecom infrastructure. So the telecom service provider has to provide more equipment. They have to provide more base stations, more cell towers, And all these things drive his back-end infrastructure itself. More cell towers, more generators. Again, these cell towers need to be powered up by a data center which hosts the servers for your billing systems, routing systems, back-end systems, and so on. So there's a huge increase in the telecom infrastructure required. Similarly, all the services we access online, the Facebook, the Google, and Yahoo, they all need to upgrade the infrastructure continuously, which results in increased amount of storage, servers, and network. So what are the challenges for the data center? So as we consumers keep on buying, new equipment, so what is not seen by most of us is a huge challenge faced by the data center providers. What are they? See, the Intel Gordon Moore long back defined this Moore's law. That means every 2 years we double the 18 months we double the capacity of a CPU in terms of increasing density or increasing power. How are these servers stored in a data center? Data center, basically we have this racks, we call it as a 42U. This is the standard size. A U is a unit of measurement in a rack in a data center. Typically 1 U is equal to 1.75 inch. So when you put servers in a rack consumes about, a rack is typically takes a physical space about 10 square feet. In a 10 square feet of area will consume about 3 to 7 kilowatts of power. I'm saying kilowatts, not kVA, it's kilowatts of power. But what is happening? The microprocessor manufacturers, the hardware vendors are coming with more and more powerful servers. What is happening with these more and more powerful servers is that in the 42U rack, with a 10U itself, I am able to consume 7 kilowatts of power. That means I have a huge rack which is sparsely populated. I am not able to fill the rack because I don't have a sufficient power to power all my servers in a single rack, which means my data center space has to increase hugely because I need to spread the rack. Either the option is to spread the rack or increase the density of the servers in the rack. Increasing the density of the servers in the rack has a big impact because electrical cables are laid long back. You can't easily go and change all these back-end cables, your generator, distribution panels. That's one part. Second part is you need to provide more and more cooling. Whatever power server consumes, you need equal amount of power to cool these high-end servers. So cooling is a big challenge today. More number of servers in the rack means you need to provide more air conditioning to cool them. It also increases noise, so weight, so on. And we look at IT, right? There are two parts of the data center. One is the IT part, is the electrical part. IT part is where we look at provisioning IT, servers, storage, and network equipment. There is also electrical capacity. It means as and when you keep on adding more servers, you need to provision more power. In terms of, you need to add more UPSs, more generators, all your distribution switches. So all the electrical capacity has to be increased, and which is not very easy. And data centers use what is known as power utilization efficiency. I will talk about this little later in the presentation. What does it mean? Data centers use only PV to measure how efficient a data center is, but it's not a good measure. How much does the power cost in a data center? So this is very, very surprising. For those of you who have not been in the data center, have a look at this last bullet item. So when you put one rack of servers in a data center, so you need power to power the servers. You also need air conditioning to cool the servers. So one rack space of servers, typically where you can keep around 10 to 15 servers in a data center in one rack, it costs about 1 lakh rupees per month. So imagine a data center of 100 racks, which is not very uncommon these days. 100 racks will have about 1,000 servers. About ₹1 crore electrical bill every month, which is pretty high, and it is not going to come down, it is going to increase over time. The EPA and NESR have done quite a bit of study across data centers in US and Europe, and they use a metric called as power utilization efficiency. That means a data center has electrical power coming in. Part of the power is used for air conditioning, cooling, lighting, and so on. Rest of the electricity is used for actually powering the IT equipment, which is the server, network, and storage devices. So this ratio of total electricity power by the power consumed by the IT equipment is called the PV, or the power utilization efficiency. So we consider a good PV is 1.4. Great one is 1.1. There are very few data centers like the Googles which have 1.1 PV. On an average, most of the power data centers have overall PUE of 2. If PUE is higher than 2, it's pretty bad. That means you are wasting a lot of power. It's very, very inefficient. If you look at the histogram of the PUEs, you see the average PUE is 1.1 across the US. It's not a great thing. You also see a lot of data centers in the range between 2 to 2.5 to 3, which is a matter of big concern because so much of energy is getting wasted. Similarly, look at the Efficient Servers Consortium in Europe. It is a study looking at the data center energy consumption and what's the impact on the dollar terms, in the billions of euros. If you look at the projections from 2006 to 2011, if data center people did not implement any IT energy efficiency, you would probably consume about 9 billion euros in energy cost itself. Whereas if you did implement some energy saving schemes, you could probably reduce it to 6 billion. And if you did very, very efficient way of use the data center very, very efficiently, you could probably cut down the energy cost by almost half. This is another study from UK, Department of Energy and Climate, which is a study of the energy cost, right? Look at 2001, take 2001 as the base, almost a 77% increase in electricity cost. And you will probably see similar trends everywhere. Solely because these data centers and IT equipment is causing indirect impact on the environment, you will probably end up paying additional expenses towards overcoming the environmental related costs. And whatever I see in UK, probably you see a similar trend either in India and US, you will probably see a similar trend. Look at data center. Second part, which is also a big part, is the enterprise IT. That means all organizations, have their own desktop, servers, laptops, a lot of IT equipment. That's also a big number. So again, Moore's law comes into play here. Every few years, the data center in the enterprise IT, we do a refresh. We buy a faster and faster equipment, more powerful equipment. Then enterprise IT consists of quite a variety of equipment. You have desktops, a lot of networking equipment, wired and wireless, printers, projectors, a significant number of servers. And recently we have seen an increase in number of devices like smartphones and tablets. And most of the enterprises do have a single electricity bill, and then for both IT and non-IT. So facilities department ends up paying the bill, and IT is not in the picture of the electricity costs in a typical enterprise. And there are no tools, no data to exactly measure how much power does IT consume, how much power should I provision to the electrical side of it. So it's either under provisioned or very often is very highly over provisioned, which means electrical capacity planning is inefficient. It's not designed to meet the IT requirements because there's no data and no way to measure how much energy is required for the IT equipment. And the part of the reason has been because there's no easy way to measure IT power. You may not look at a single desktop or a server. You have keep on buying hundreds of equipment over years. You have so many brands, so many models, and it's very hard to measure. And you look at a CIO dashboard, power consumption, CO2 emission is not in the radar. You just look at a business metrics, business revenue, top line, bottom line. Somehow this power is not in the radar, but I think just a matter of time, power and CO2 emissions will be one of the business metrics or the key KPIs of CIOs. Let us look at the challenges in the data center. We looked at what are the challenges, changes and challenges in the enterprise IT. Let us look at what are the changes happening in the data center part. Challenges. Again, Moore's laws continue to drive. I said, the rack density is increasing, just creating a lot of challenges. Electrical IT capacity planning is an issue, and data center bill, power bill is rising. I said this, as of today, it's 1 lakh per rack per month. It's just going to rise over time. So what we see today is there's sort of a crisis, in the dilemma between IT and energy. So what can we do about resolving this energy crisis? So there have been studies done by various institutions around the world. Just look at many of the enterprises just simply buy a server. It may cost couple of lakh rupees to buy a server, but nobody worries about how much does it cost to operate the server. Recent study done by a Gartner says that if you buy a typical x86 server, the power cost over 3 years exceeds the cost of the buying a server. Typically, this power cost is a facilities cost, it's an operational cost. Somehow it's not calculated, it's not a part of the IT budget. We think we need more servers, we keep on buying servers, indirectly eating somebody else's budget and causing impact on the bottom line of any typical organization. So seen the power exchange, energy players keep changing very, very often. And let us look at the other aspect, many of us are party to it, every day you use desktops at home, offices. As per the research done by climate savers, a desktop wastes almost 50% of the energy. It is very surprising and shocking. And recently the New York Times carried a very interesting article about data centers and energy efficiency. And McKinsey also did a study on the data centers power consumption. So if you have data centers, you have hundreds of servers and storage equipment. How much of them are really used at all times? And it's shocking to see that only 6 to 12% of the electricity is used for powering the actual equipment which needs to service the end consumers. There's a huge wastage of electrical power in the data center. And you just see the quote, the other mention from New York Times that about the toxic air containment inventory. You see, if you are generating about 10 kilowatt, consuming about 10 kilowatt of power for every rack in a 5,000, 10,000 square facility, you will be consuming megawatts of power. And if you do not have any grid power is off for some reason, if you are running a generator, you are causing huge amount of emission. A typical small data center in any organization can in fact power an entire neighborhood, of hundreds and thousands of homes. So what is happening is these data centers are small concentrated islands of toxic air and energy, high consumption of energy. And why do we need to save power? We have seen that there is huge amount of wastage. And how does the wastage happen? Basically, if you look at the way the power is consumed, right? If you look at the complete chain, so you have a server. How does a server draw power? A server component uses DC power, the direct current, and you have a SMPS equipment within the server which converts a rectifier and SMPS converts AC to DC power. So there is a power loss there. Then you have power distribution panels, right? Distribution switches and panels within an enterprise data center. There is a power loss there. You have UPS, again inline UPSs are used for servers, so which again inline UPSs take AC power, convert AC to DC, again use the inverter to convert DC to AC. So there is a power loss there. Again you have cooling. You need air conditioning to cool the heat generated by your IT equipment. This of course is a transformer in the building from where you draw the power and the switchgear equipment. So you see amount of losses everywhere. Which means if you are consuming 1 watt of power in a server, actually the total power drawn from the grid is equal to almost 2 to 3 watts. And this does not include the transmission and distribution losses which happen all the way from the source of electricity generation. Maybe it's a power plant, hydropower plant, or a nuclear power plant, or a thermal power plant. Already in this country we already have high double-digit T&D losses. So if you combine all these things, it's very, very imperative that you just have 1 watt of power in the server. It has a huge cascading effect throughout the chain, all the way to the source of power generation. So coming back to the intelligent power management. Why do we need intelligent power management? See, we know that power can be saved. Why are people not saving power? That's a big dilemma, right? There have been many approaches towards saving power. Many of them have not succeeded. Let us go look at a list of traditional power saving techniques. and what is the impact of that? As we saw the the Gartner reports and the McKinsey report that a lot of equipment is not used. Climate Savers mentioned that 50% of the time the desktop energy is wasted. So then what can we do about it? So there are generic core optimizations built by the hardware vendors, the chip manufacturers, OS vendors. They're very proprietary to a specific chip or a OS. It's not easily scalable. Many times, many of these are intrusive. That means you enable power saving mode in your smartphone, a tablet, or a desktop. It disrupts your usage. For example, just take an example of a small standard desktop, right? Running an XP desktop or a Vista or a Windows 7. You enable power saving mode built in for the Windows itself, operating system itself. So doing a presentation, just as I am speaking now, it looks at your, you're talking, your keyboard is idle for some time, it turns off the display. It is sort of intrusive. Very often you must have seen you're doing a video chat on a Skype, you don't use a keyboard. The system thinks that you're not using the keyboard, it's idle, it turns off it. So what we call as intrusive. And again, that's one issue with respect to the duration power management. The second issue is again, whenever you try to implement any power management, the system becomes slow. So these are the two main reasons why people turn off power management or do not use power management. And last but not least issue is about measurable. It's not measurable. How much power am I consuming? So we are not even metering our equipment. There's only one big meter in the entire office, which nobody has time to go and measure it. There's no automated way of measuring the consumption. You can't measure how much power can be saved in every equipment. So these are the typical challenges why traditionally the power management has failed in the IT industry. So what do we look at today? We look at what is known as IPMPlus or the intelligent power management or something more. So what we say is that power management cannot be a generic formula applied across enterprises, across users. Power consumption usage of a system depends on what business you are running, how you are using the system. So to be power management has to be tailor-made to every type of business. We also have what is known as application census. What does it mean? Depending on what you are doing, let's say I am downloading a file, internet, I am downloading a 1 GB file. It may take 3 hours. It may take 3 hours. But I may want to go away from my desk. When I am back in my desk, download should have finished. But when I am not using a computer, the display can be turned off, right? Intelligently the display can be turned off, whereas the download can proceed. Or if I want to do a download overnight, because my the ISP provides unlimited downloads overnight, I should be able to schedule start a download before I go to bed. Let it go on for 4 or 5 hours. When the download is finished, the system should be smart enough to figure out nobody is using it, the download is complete, should automatically turn off the power. Another important thing is, how do you define this power policy in a large enterprise? If there are hundreds of thousands of users, different departments, different buildings, I should be able to define policies, power policies. I should be able to apply the enforce the policies, measure who is using more, which devices are used more often, which are idle more often. Should be able to centrally define a policy and enforce a policy. That means during lunchtime, example, lunchtime users are awake for 1 hour. I want the device to go into sleep mode. When the users come back from lunch, the device should be working normally. Users typically leave the office at 7 o'clock in the evening. So when the users leave off, I want to make sure that all the devices are turned off. Again, when the users are back next day, then probably users can turn on. Or otherwise I can look at automatically turn on the devices. And I should be able to do also fine grain. So when if you look at a typical desktop or a server, you have a CPU which consumes power, you have a fan, you have a disk, a lot of peripheral devices. We need an intelligent way of turning on only those devices which are required and turning off these components which are not required. So we can save power by turning off devices when the devices are not in use intelligently. Same time, within a device itself, we can intelligently turn off certain components of a device so that we can continue to save power. For example, I'm just doing this webinar, my laptop presentation. I'm just using the display and my mic. I'm not using the USB port, I'm not using the hard drive. So these devices are turned off when they are not in use. Again, power savings are quantified. So you should be able to measure power savings. How much power did I save? Where did I save? Where am I saving? Where is my power wasted? So that I can fine tune my power policies or keep on optimizing the power policies. Look at the market today. We have, you have mobile devices, desktops, laptops, mobile phones, ultrabooks, and you have backend servers. So as a part of the IPMPlus suite, we have three kinds of offerings. The mobile edition, which is basically meant for your handheld devices, smartphones, tablets. The PC edition meant for enterprise desktops, where you can centrally define a power policy and manage a multi-location site from a single place. And we just have seen about 30 to 50% power saving across the globe. We also have a cloud edition. The upcoming cloud edition is meant for data centers. And one of the challenges we do see in a data center is that there's no metering in place today. You have a wide variety of devices. You may have servers from HP, Dell, IBM, Sun, so many vendors, different operating systems, different UPSs, different PDUs, and so there's a wide variety of diverse equipment. So one of the important things in an enterprise or a data center is to first identify what IT equipment do you have. Find out which are the IT equipment in use. Very often there are, with the wired and wireless connection today proliferating in all enterprises, there are a wide variety of equipment. It's not easy to find out what is being used, which device is on when, how many devices are on at a point of time, so on. So our approach towards intelligent empowerment has been use a fine-grained approach, as I talked about. You don't try to turn on the equipment itself. Sometimes the equipment may be in use, but you want to turn on a part of the equipment, when it is not in use. Then it should be non-intrusive. That means user should be still able to use the equipment, should not impact the user of the equipment itself. Next thing, it should be distributed. You have a wide variety of equipment which are networked today. Your desktops, laptops, servers, smartphones, printers, projectors, they're all networked. So we do have a US patent on intelligent power management. So the approach towards intelligent power management is to discover the IT assets in an organization or on the IP network, then measure how much power is being consumed today. Identify which are the equipment which consume more power, which of them are idle, which of them are not required. So by measuring and doing analysis, you'll get a fair idea of what kind of power policies are applicable. What's the usage pattern? Is the usage pattern same in a department, or it's different across different departments? Once you have measured and create a baseline, how the power usage pattern, you can do analysis of the usage pattern, then define policies. You can probably define. You may end up finding out the usage is similar across all departments. You can have one policy, or you find out that your usage is totally different across different departments, different buildings, geographies. You can create custom policies to suit every group of users. So once you create custom policies to apply the policy, you start seeing the savings. At the same time, while this energy is being saved, system continues to give you a report of dashboard of how much energy is consumed, how much is saved, and is there any further opportunity to optimize the savings. So if I see the savings is a continuous process. Measure, analyze, and save. You achieve some savings. There's still possibility to optimize the energy consumption, at the same time not impact the user experience. What you see here is sort of a CIO dashboard, right, which shows a real-time monitoring of all the nodes. So a node could be a desktop, could be a server, could be a handheld device, could be a UPS, could be a printer. So at any point of time, the whole dashboard is designed from IT and energy perspective. So you get a real-time status of how many devices are on, how many are off, how many are in the sleep mode, how many inactive. That means they could be turned off, they're no longer accessible. You also have get a set of events on whenever a device comes up or goes down. You get a dashboard of the power consumed and saved. Other important aspect is where we try to integrate IT and electrical energy. Basically, you need to know what is the peak load on your IT systems, and also the peak load from the electrical point of view, and what is the average load consumed per node. A node, I assume, could be a desktop or a server. So we do have a sort of a soft meter this soft meter can actually get a data by doing a mathematical modeling of the various IT systems, or if you have a energy meter which is on the network, the software can pull the data from the energy meter and show you real time what's the peak energy consumed, what's the energy consumed. Same time, you get a detailed report of power consumed, day by day, month by month. You can see the power consumption, savings, and as you see that, if you see the savings are less, you can go and drill down and find out why is the savings less. Has the power policy, can I, has the usage pattern completely changed, or can I, has new equipment been added, or what else is going on? Actually, you can go and do a root cause analysis and figure out the cause for this increase in consumption or reduction in savings, and fine tune the policies. So what we suggest is that you adopt intelligent power management, can actually cut down your power usage significantly, can actually make your IT go green. Sorry about that. So this ends my presentation. If you have any questions, be glad to take that.
Thanks for the insightful presentation. Let's quickly take up the questions now. Mr. Srinivas, please read out the questions and their answers so that all our users may listen to the commendable insights.
Okay. The first question is about, by Isha Priya. Question is, please explain the relation between U and inches and power. Okay. U stands for unit of measurement in a data center. So we have a rack, we have a measurement, and the various equipment which you put in a data center, they all measured in U's. For example, servers, you have 1 U server, you have 2 U server. So U is a unit of measurement. Approximately 1 U stands for 1.75 inches. So we have a rack of 42 U. Probably you can populate about 40 units. Leave some space for cabling and other wiring. So if you have 10 1 U servers, can probably easily fit into a 42 U rack. U does not really have a relation directly to the power. Indirectly the relation. Basically, in a 42 rack, typical power you can consume because of the electrical limitations is about 2 to 3 kilowatts on a normal data center. Where there's a high density data center, can probably consume 8 to 10 kilowatts of power in a single 42 U rack. The next question is from Sabiba Ahmed. Please tell USB port and hard drive port power consumption in a PC. The USB again changes from USB 1.0, 2.0, 3.0. USB is about is a few watts of power. That's what it consumes. A hard drive can consume anywhere between 5 watt to 10 watts of power. The next question is from Abhay Master. The question is, what is the impact of virtualization or power consumption? It's a good question. Actually, one of the purpose of virtualization is to optimize the power consumption. So just let me take an example. If we have, let's say, 3 servers, 2 CPU servers. So totally you have about 6 CPUs, and you found that utilization about 30% in each of the 3 servers. Possibly, what you can do is when you can put a higher capacity server, let's say a quad core or a higher capacity server, move all this applications on three different physical servers to one large server. So virtualization does help you in optimizing power consumption. How virtualization does is basically it tries to improve the utilization of the servers. Instead of having 3 servers at 20-35% utilization, I combine all these 3 machines, physical machines into 3 logical machines into a large box, which is more power efficient. The next question is from Subramanian Seke. The question is there any application on Linux OS itself with schedule based sleeping mode? The OS itself doesn't have anything as such because there are some fundamental issues in the Linux OS itself. So there are, you can only write a small cron job or a script to do some basic things, but the OS itself doesn't have any sophisticated way of scheduling for power on, power off. The next question is from Koteshwara Rao Venkata. The question is, does virtualized environment consume low power? See, the virtualized environment itself will not consume low power. By doing virtualization, you are eliminating, instead of having 3 or 4 physical servers, we are combining the 3-4 physical servers into one large box. So by doing this reducing the number of physical boxes and increasing the utilization of a single server, you are reducing the power consumption. So indirectly, actually, yes, the virtualization helps you to reduce power cost. The next question is from Ashok Damelia. The question is, how IPMPlus works with printers? See, if you look at a printer, you have a wide variety of printers, right? You have inkjet series of printers, you have laser printers. And of course, the laser printer, laser multifunction printers consume a lot of power. And these laser printers are on, depending on the model and the brand, you may consume anywhere between 200 to 500 watts of power. And when you are not printing, these devices can be put to sleep mode or standby mode. And end of the day, you can actually even turn off the device. Even when you standby mode, again depends on the model and the brand. Some devices consume 50 to 100 watts even in the standby mode. There are some brands consume few watts of power. So the way IPMPlus tries to save power in printers is to put them intelligently into a sleep mode or standby mode when the printer is not required. Yeah. The next question is from Deepesh VP. The question is, can you explain intelligent power and grid modernization? Yes, it's a very good question. See, when you are trying to modernize the grid, one of the challenges we have today is the peak load. Okay, the average to peak load is the issue. There are many sources of power. Your electrical, thermal, nuclear. You can't change the power. You can't change the load generating capacity dynamically. But if you have intelligent power management throughout the IT infrastructure and non-IT infrastructure, actually you know the power consumption, power usage pattern, so you can align your grid power usage, the generation can be aligned with the consumption. So what the smart grids are trying to do is basically intelligently figure out when to turn on, when to turn off equipment. At the same time, once you have this pattern, what equipment is being used when is the power required. So right from the generating source to the complete distribution in a unit, you can intelligently turn off various components and start optimizing the savings. The next question is from P. Kalyan. The question is, we are using nearly 1,500 systems 24/7. These systems are switched on. Is there any program to change power mode because we are working only 10 hours per day? So there is no actual standard program itself to globally change for this, this 1,500 plus systems. That's why we built this tool called IPMPlus, where you can centrally define policies, and in a 24-hour period, it can be turned on only for those hours, 10 hours, which is required, and you can possibly say about 14 hours of power for all those 1,500 systems, which is a huge saving. Next question is from Anand K. Is how do you overcome the latency while switching back from power off standby mode to an active mode? Today's equipment so basically again it depends on the application and what kinds of applications you are running. That's where we need to have this intelligent power management. You need to define rules or policies when you want to move from so there are again in standby modes, there are different standby modes. You can actually keep you can keep the server on when in a very, very low power mode. It can react in microseconds, or you can actually keep in a standby mode. Today, the new generation of servers and the desktops are fairly efficient. Actually, you can move back from a standby mode to an active mode in a matter of seconds. And power off mode, again, it depends. Power off mode certainly takes time. So you may not want to turn off. You may want to probably hibernate. And starting from a hibernate mode is much faster than rebooting the equipment or turning off from scratch. Again, which mode you want to turn on? Switch on from fully active mode or a partially active mode, full standby, partial standby. Again, depends on the scenario, and you need to set the right set of policies so that your response time is not impacted.
I think there are no more questions, Mr. Srinivas. Thanks for the insightful presentation, Mr. Srinivas. I am really thankful to Mr. Srinivas for conducting this webinar. It was indeed a great session. I would also like to thank all our participants for their support in making this webinar a success. The recording of the webinar will be available on techgeek.com by tomorrow. Thank you all.